Okay, let's get started. So today we're going to be talking about indexes, new topic. Announcements. Homework 4 was posted yesterday. Midterms are graded, but they're not like all tabulated yet. So those grades will be posted soon. And not you can pick up your exam from my office hours. I guess not today because I don't have them yet, but starting on probably Wednesday. I'll send out like an announcement, I guess, once they're actually. Let me put it another way. Once you see your grade on Canvas, that means I have your exam, and then you can pick it up. Okay. And of course, Friday's the last day to drop the class, and let me know if you have any questions about how your numeric grade might translate to a letter grade. Okay. Questions? No. All right. So today we're going to be talking about indexes, which is like a performance-related topic. So to motivate that, I'm going to talk just remind you all of the fact that computers have many different kinds of storage, and those different types of storage they exist because there's like a trade-off between delay and capacity in a computer system, right? So here, this picture on the upper right is a like lithograph of a CPU core or CPU. IC. So it includes like 8 cores in this case. So each of these little boxes that says core is where the calculations actually happen. And the closer the data is to that location, the faster it's going to be, because that's where the actual calculations are happening. So there's a little bit of space within the core for some for registers. So just a tiny bit of storage, 1 kilobyte. And those are really close to where the calculations are happening. So the delay is tiny, a fraction of a nanosecond. Then a little bit further away, like on the side of the core, for example, there might be a level 2 cache where you have more space to store data, but it's a little bit further away from where the calculation is happening. So maybe the delay is 5 nanoseconds. And then you have a level 3 cache, so there's more space the further away you go. So over here you might store some data, and that's a little bit slower to get to. And then eventually you might leave the CPU chip, and go to a RAM chip that's across the motherboard. Of course, that's even further away, therefore slower to get to, but there's more space for there to allow you to store, like, let's say 16 gigabytes of data there. And yet further away, you might have a solid state drive, and you're using different types of transistors in here, so that gives you more capacity than RAM, but it's slower and it's further away. And the interconnection is different, so there are fewer pins sort of on the SSD than there are in the memory. And yet furthest possible location away is the magnetic disk in the computer, if you have one. I guess these days laptops don't usually even have these, but a desktop computer or a server would have a magnetic disk, and those are really slow because they have to spin around before getting to the location where the data is, but there's a lot of capacity there. Okay, so hierarchy of storage. Some storage is slow to get to, yet we want to efficiently analyze big databases that need big storage devices. Okay. All right. So here, notice this is an animated GIF, which I'm proud of. I was able to find this and put this in the slides. Okay. So storage has limited bandwidth. Although the capacity of, say, a disk is quite large, at a given time, the computer can only access the data that's underneath this read arm that you see moving back and forth. So if the data, this magnetic platter has bits encoded on all the different locations on the platter using magnetic charges, and to read those charges or write those charges, the disk has to rotate to the right angle, and the arm has to move like angularly to get to the right position, right? So there's that mechanical action in 2 different dimensions is required before reading, and also at a given time, just a small fraction of the data on the disk is available to read because it's only the data that's underneath that tiny little sort of razor sharp read head here. Most of the data is not accessible. You have to kind of like seek. You have to move physically to the particular location to read the data. The same is. Does that make sense? By the way, so we have a lot of data on here, but it's kind of all locked away not locked away, but it's like it's hard to get to all of it because you have to like painstakingly move this tiny little read head across this entire really big surface to get to all of the data. And this is a tiny, tiny, tiny little read head. Similarly, RAM, which is, let's say, like the memory in the computer that gets cleared when you turn off the computer, also can store a lot of data in these chips. Not quite as much, but there's a lot of capacity in these chips, a lot of transistors on here where you can store charges. But there only a few bytes can be transferred at once because the interconnection between the RAM and the rest of the computer, like the CPU, is just these couple hundred of electrical connections here on the edge of the card, right? So there's only a little bus technically, but like, just a couple hundred wires that allow you to read values off of. So if you want to read a lot of data, you have to they all have to take turns going through this little channel. It's kind of like a narrow little road that everything has to go through, like a bottleneck. If you want to read all the data off of memory, it all has to take turns appearing on these few electrical wires here. So you have to and there's only there's a limit to how quickly you can change the values on these connections, like a few gigahertz, or megahertz, depending on the memory. So you're limited in how quickly you can read the data off of this type of memory. Even though there's no mechanical limitations, there's like limited electrical bandwidth, so to speak, there's a limited connectivity between all the billions of storage locations on these chips and the outside world, which has to view it through just a couple hundred electrical connections. Okay, so both of these types of devices have limited bandwidth. SSDs, by the way, these are disks that are based on transistor-based storage technology. Same idea as RAM. You have a lot of data locked into flash memory on chips and transistors, but then to access those, you only have a few electrical connections. You can see even fewer electrical connections on the SSD. So you have to take all those bytes have to take turns being transferred over that narrow little interconnection to access it. Okay, so that's why storage is big, but it's has limited bandwidth. Like you can't access all of it at once. You have to take turns accessing just little bits of it. You have to scan through it, in other words, if you want to view all the data, right? And that takes a long time. Simple concept, but maybe not entirely obvious. So more abstractly, if we look at computer storage, on the left-hand side, I'm showing like memory. This could be also like permanent storage, like a file system, like a disk. But here I have an array. We can view generally storage can always be thought of as an array with lots of locations where we can store values, right? So here we have addresses going from 0 up to like 4 billion. This is just hexadecimal notation, so the values go from, after you get to 9, you go to A, then up to F. That's not important, though. You can ignore that. But in this yellow region here shows all the different locations where bits can be stored, and that's the data. Okay, but the computer can only read or write from one location or address at a time. So that's kind of what I was saying before in this physical view, where you only are like with a magnetic disk, you only have this little needle sharp read head at one location at a time, and similarly you can only transfer data across one kind of chunk of data across those electrical pins at a time. So although we have all this, as a human we can look at this and see that there's a lot of data in there and we can read all the data from the picture. The computer can't see all the data at once. It has to access it using individual addresses. So memory is like a black box to the computer, or any storage is, I guess, where you give it an address. Like, for example, you might want to request the data at address number 23, and then the response you get is that there's certain data, in this case 49, is stored in address 23. And you have to do a sequence of those operations to access data. You can't just look at it visually and see that, here are the 10 different values in there. You have to kind of think about a series of individual operations accessing different addresses. Does that make sense? Just a very abstract view. I'm trying to motivate the fact that the way that performance is limited in a database is based on the fact that storage is big, but it has to be accessed in very small pieces at a time. And primarily, you can think of it primarily as being due to the limitations in the way that these things are connected to the outside world or visible to the outside world is limited to just tiny windows of data at a time. Okay. Yet, so despite the fact that we can only access a tiny bit of data at a time, we can use these big storage devices to assemble massive databases. Okay, so for example, here's a picture of a database server. Microsoft SQL Server in this case is a software that's running on this, but it's a big computer that I was working with a couple years ago at Northwestern. So it's a big like closet-sized rack of machines where there was 2 database servers, but basically you have a server here and then a bunch of like storage arrays. These are all just boxes holding disks, basically. So there are 264 disks, magnetic rotating disks in the system, all connected to one computer, basically, right? And there also were some slower disks for backups. But basically, so in total, this is 150 terabytes of storage. That's probably like 50 times what you'd have on a laptop, and or 100 times, depending on whether you're using SSD or magnetic. And they're all connected to one computer, but they're actually in many different boxes, different chassis, because a single computer isn't big enough to hold all those disks. But they're all kind of like wired together. In the back, you can see that the main computer has all these big SAS cables that connect to other boxes, other chassis that have lots of disks. And so there's a lot of data in the system, but it always kind of has to funnel through these little wires, and you can only access little bits of it at a time, so to speak. Okay. So in this class, we're going to start working a little bit with some bigger databases. And an example of one you'll work on is the Stack Overflow database from a couple years ago. So Stack Overflow is a website, like a question and answer site for programming, which I'm sure if you've done any programming at all, you probably would have run into if you did a Google search for like, how do I fix this error in Python or R or whatever, right? They actually made their data open source. They make it available, so you can download a copy of all their data, basically. So I downloaded 150 gigabytes of Stack Overflow questions and answers. That include 30 million posts, 55 million comments, basically in a replica of the entire website as of like a year ago or a year and a half ago. So it's a lot of data. If you wanted to read through all that data sequentially, if you want to read through all of it, it would take about 17 minutes, right? So obviously, when you want to be able to do queries and do analysis on this database, but you don't want a single little operation to take 17 minutes. That's way too slow, right? And similarly, if you do a Google search, or if you do a search to look for Python errors or whatever, you don't want that to take 17 minutes either. Stack Overflow wants to be able to present its web pages backed by the database in a split second to be able to find the relevant data. Okay, so the story here is that it's impractical to scan through all the data to find what we need. I mean, with the databases you've been using so far on your computers, you can just scroll through and visually you can see all the recipes and all the customers and orders and stuff. Those are tiny, tiny databases. For those ones, it's okay to actually scan through everything. You don't have to think about performance too much, because the computer can do like a billion things in a second, no problem. But even at the speed with which computers operate, this amount of data it takes lots of like human scale time to work with, right? So we need to be able to quickly find data of interest and that's called indexing. So that's the main topic of today, and that's the general idea is avoiding looking through everything to find the thing that we need. Okay. Any questions so far? So far, it's pretty abstract. Okay. So we know that when we have lots of data, we don't want to look through all of it. We want to be able to find quickly particular items where the details for particular items that we need. We know that we have to make requests to individual address locations. We can't somehow check all at once the entire memory or the entire storage. Like, we can only access little bits of it at once. Then that's why it's slow, because to scan through the whole thing involves just like requesting little pieces at a time. So to address this problem, I'm going to start off by talking about like sort of a human approach to this problem, make an analogy, and this will kind of connect to databases. And that is the idea of sorting and using binary search. So this is a picture, of course, of a dictionary, right? Which I don't know if these days, if you all have seen these things called books that are on paper, but when was the last time you actually used a paper dictionary? I had one of these at my house, but anyway, it's obsolete, right? But I think you know how it works, right? You have a bunch of words here that are alphabetized, and if you want to find a definition for a word, you find it somehow. You find the location of the word, and there's some details in there, right? So why is this an efficient system? Why is it easy to find a word? It's ordered. What about the ordering makes it easy to find the word? So if I'm looking for the word database, how do I know where to find database? So okay, so the things I'm looking for, the keys, like the word database has this like letter at the beginning, D, and I know that D fits into an ordering of all the words, and I have an idea that somehow the words in general are like somewhat evenly distributed across the whole alphabet, and so D is going to be somewhere near the beginning, but not at the very beginning. So it's going to be like maybe 20% through, right? So if I flip to 20% through, I found some D words, right? That's kind of a very rough description of how it works. But that's not precise enough to translate into like a computer program or something. If I wanted to okay, let's put this another way. Let's say that if I wanted to write a computer program to find a word, what would be a way to do that? Yeah.
Start in the middle.
Yeah, you start in the middle. So honestly, I think this is probably a concept that if you've seen some programming, you might have run into it and doing so would it's not necessarily something I think you would come up with automatically, but looking in the middle is a good way to approach this problem, because you can look at the words here in the middle and make a decision about whether the thing you're looking for is before or after that. Right? So we have like Louis d'Or and Love Potion, and those start with L, and so those are greater than database. Therefore, I know that the word database is in the left half of this dictionary, right? It's not. I can actually rule out all these right-hand side pages and continue my search across these pages, right? So in one step, I've cut the search space in half. And I can actually take this remaining half and do the same thing, break it in half, and look here, and I find, if I look here, doji, I don't know what that means, a motherless calf, okay, Western U.S. So database is before doji, so I throw out the right half, and I'm left with this like 1/4 of the dictionary. And okay, at this point, if I'm a computer, I'm going to proceed kind of in this dumb way. I know, as a human, I know it's probably going to be pretty close to where I am, so I could like skip. But if I didn't know that, and particularly if I didn't know the distribution of words across the alphabet, like if this wasn't a dictionary of all the words, but just a random subset of the words or something, or if these were like names in a particular language I wasn't familiar with, I wouldn't know necessarily how popular the different words were. So I could just, but one way that I can be sure that I'm at least making good progress is by always going to the middle, right? So here I go to the middle, I get some C words, and I know that now I can throw out the left-hand side because C is less than database, and I go to this half and so on, right? I keep doing that, keep looking at what's there. I get closer, daemon, that's actually, I shouldn't have thrown out. I was a little sloppy there. I actually got to one that's greater, so I throw out the right-hand side and keep going, and eventually I will get to the word database. Yeah, and like eventually I'll get to a page and I'll have to like go within the page, but that's the idea. So that's a binary search actually. All right, so we have a sorted list, like a printed dictionary or a phone book or something. We can use binary search, and that involves looking in the middle and kind of throwing out half the results in every step. And it turns out that because we're always throwing out half of the remaining results, we know that the number of steps it's going to take if there are n entries is log base 2 of n. Because if you kind of take it in the reverse order, like if you have if you know that you're going to go through k steps, the number of entries you can cover, it's like doubling each time. So 2 to the k is the number that the original list could be, and the log is what gives you that number of exponentiations it takes to get to the number. So for example, if we have 4 billion entries in our list, that would be like a phone book with half the people in the world. It would only take 32 steps to do a binary search to find a particular entry, right? That's actually really pretty quick for a huge list. We know that because 2 to the 32 is about 4 billion. Exponents grow really fast, right? And so in that first step of the search, we would be throwing out 2 billion entries, right? That's really good, right? All right. So these steps here just formalize what I said before, where you look in the middle and you either recur on the left side or the right-hand side, repeating the same operation. All right. So binary search with a sorted list is pretty intuitive, but it's not enough for a couple reasons, right? So the first one is that you can't really sort in multiple dimensions. Like this dictionary is sorted according to the words. It's not sorted according to like the part of speech, like verbs and nouns. If I wanted to find all the nouns in this dictionary, I would have to go through all of them. Or like there are other things in here, like see how this one here says informal? If I wanted to find all the informal words in this dictionary, I would have to scan through all the pages and check each one to see whether it said informal and include those in the list, Or if I wanted to find all the ones where the definition included the word, leather or whatever, that would be really slow because that thing that I'm looking for was not the one thing I decided to sort by. The one thing I sorted by was the name of the word, and that's the only thing I can efficiently search for, right? So sorting is limited because you can only sort in one dimension. Another limitation here is if you think about this as being a computer data instead of a book, it's difficult to insert new data or remove data or modify the data without shifting everything else to make room or to reclaim room, right? So if I suddenly wanted to delete dead weight from this dictionary because I think it's dead weight, I would either have like a blank space here, which is wasteful, or I would have to take the I would have to take the data below it and like copy it up one level and take the next one, copy it up, and so on and so forth, right? That would be really slow. I'd have to go through like all of these pages, if this is memory, all these memory locations, and copy and like read and write every single one of those just to make this one tiny deletion. That's really slow. If I wanted to add a new entry, I suddenly found a new word to put in here, I would have to do a similar thing where I like what started at the very end and like shifted everything down to make space. And that again, that would you'd have to go through basically on average half of the entire data set to do that shift, right? So shifting is bad, it's slow, but you have to shift if you want to maintain if you're relying on the ordering of the data itself as the way that you're finding things efficiently, right? Another less important problem, this third point, is that this binary search over the full data set doesn't take advantage of the hardware storage hierarchy. I think to understand this might require a little bit of computer engineering, CPU architecture knowledge that we don't have time to go into. But basically, the caches, the CPU caches, these higher level parts of memory can store a little bit of data, and they generally can it's easy for them to store contiguous data from memory. Whereas with the binary search, you're like jumping to totally different parts of memory each time you're doing an operation, so you're not making use of the cache. If you could somehow take all that information you're using in the binary search and squeeze it into a small amount of memory that was contiguous, you could put that in a cache and work very efficiently. But that's kind of I don't think we have time to get into why that works. All right, so one thing I claimed that you couldn't sort in multiple dimensions. That's not totally true. I mean, so it is true, but there are ways you can get around that. One way that's done, I have an example of that in the Granger catalog. So if any of you have worked in, I don't know, scientific experiments, or they just have a lot of weird industrial equipment in here. Like if you worked at a factory, for example, this would be a catalog where you'd order little parts for maintenance and for little gizmos and switches and motors and stuff. It's a huge catalog, and they want customers to be able to access all the different entries efficiently. So the solution that they have to that problem is, okay, first of all, they do have some kind of ordering. The products are ordered according to category. So they order things according to category, but they don't just do that, because they want you to find things not just according to category, but also according to the manufacturer and the product type. So to deal with that, they have secondary indexes. So okay, this is the kind of stuff that's in here, like painting sprayers and stuff like that. Okay, anyway, but in the middle here, you see these yellow pages are a product index. So here, in alphabetical order, they have all the different types of products, like cement, center, ceiling fan, caution signs, caution tags, caulk guns. Okay, so if you're looking for a particular product, you can go to this yellow section and find it using a binary search, right? Because this is alphabetized according to the product name. And then from there, there's a reference, which is a page number, that gets you to the data to where the data really is. Like if you want to see the price and the picture of the product and all that stuff, you start off here in the index, and that's organized so you can search according to the product type. It lets you find things, right? And there's even a second index here in blue. There is a manufacturer and brand index. So if you want to find all the things made by Wolo, they make both horns and vehicle lights and backup alarms. Those are going to be in different parts of the book because, again, the book is organized not by manufacturer name. It's organized according to the categories of products, and these are different categories of products. So these references here. So these blue pages again are organized alphabetically. These are sorted according to the manufacturer, a different type of sorting, but they have references to the data itself that's organized differently. Okay, so there are three different indexes here essentially. The main index is the main ordering is by product type. And then they have these secondary ones which are products and manufacturers. Does that make sense? So this is a kind of intuitive solution to this problem for this data set here. So that works for this catalog. Why would that be a poor solution for a database? So yeah, actually it's not a terrible solution for a database. You could think of this as a database. If this is a database table of products, it has three different ways for you to find things efficiently, right? But what about it is a less than ideal solution? Remember I mentioned with the dictionary, one of the problems with that was one of the problems with the dictionary was that I couldn't add or remove items, right, without shifting everything. So the same is true here with this Granger catalog. Because there's just three different sorted lists. I I can add to the indexes, I guess, with doing. I still have to shift. It's less shifting because those are like an abbreviated. It's not the full data. It's just references to the data, but it's still a pretty big set of pages that has to be shifted. So the main problem with the idea of just sorted lists, even if you can keep separate lists that organize things differently, but you can't add, delete from those lists efficiently without shifting things. Does that make sense? Okay. All right. So the solution to this problem in databases, so it's the same idea of indexing applies to databases, but we tend to use these things called trees or hash tables, self-balanced binary trees, or even not binary trees, self-balanced trees in general, and hash tables to index the entries in the database in a way that allows this indexing structure. This thing on the left is the index somehow, and it's not just a sorted list, it's a dynamic structure that can be efficiently added to and removed from. And we're not really going to go into the details of how to build these data structures. That's what classes called data structures are for. So CS 214 covers that these things in detail, and it gets pretty complicated. But the idea is that you can create a structure in memory, in the computer storage, that is not so like reliant on position as the sorted list is, but still allows you to navigate through it in a way that allows you to quickly find things. It doesn't use position in storage to represent anything. It uses pointers to connect things up and allows you to add and remove things efficiently. So here's an example of a balanced binary search tree. So if you have a bunch of numbers that are like in your data set, and you organize them like this in this tree-like structure, where you have a root, which is this first node, and then every node can have two children, a left child and a right child, and the left child has to be less than the element, the right child has to be more than the element. And by organizing it in that way, you can quickly find whether an element's in the set by like starting at the top and just going left or right, depending on whether the thing you're looking for is greater or less than. So it's very much like the binary search, right? You start kind of in the middle and you move one way or the other. And every time you move, you're eliminating a part of the subtree that you're not going down. So if you move left, that means you've ruled out all the stuff on the right. And from 17, if you go right to 23, you ruled out the 9, 12, and 14 on the left-hand side. Same idea as binary search, except you're using a tree. The point of organizing it in a tree is to allow you to like not rely on the position of these things in memory, but just the references between them. Like the arrows are pointers, which is like, in this node here, you would store what location in memory is the left child and the right child. But again, the details of that would require a data structures class. And for these to be balanced, if these are balanced, like in other words, it's not like you actually have you're not just having like one path that has data as opposed to like both left and right. If this thing is balanced, then you'll find that the number of checks you need to do to find an element is still log base 2 of n, because as you go down the levels, you get exponentially more elements, because you get twice as many elements each time you go down. Okay, that's a balanced binary search tree. And so that's one of the types of indexes we can create in a database. Hash tables are similar but different, and I'm not going to talk about them. Okay, so indexes, we actually already get indexes in all our databases when we create a primary key. So primary keys are actually a type of index. The words index and key are kind of used interchangeably, actually, in a lot of databases. The reason why, so remember, a primary key is a value that has to be unique for each row you add to the database. So it's important that we can quickly do that check. So if you're ready to add a new row, and you're saying, okay, the primary key for this is going to be 14, and here are the other values, it would be nice if we could quickly check to see whether 14 is already present so that we can quickly like reject or accept that row, right? In order to do that quickly, we can use an index, right? So primary keys are always indexed, but those aren't the only things that are indexed, because you want to index things not just to do these uniqueness checks, but also to make queries efficient. So if you happen to always be checking in a particular table for entries that have, like, for people who live in a certain state, if you're always doing that kind of a query, then for example, it might be helpful to index the state column in that table. Otherwise, you have to scan through all the elements to scan through all the rows to find those rows that have the state being equal to whatever state you're interested in. Right. So by default, if you do a query, the database management system will have to examine every row in the table to find relevant rows. If you have some kind of where condition, or you're doing a join, a join is like a where in the sense that it's looking for elements that match some criteria. And doing those full table scans can be slow, would be slow if the table is big. So the whole point of adding indexes is to avoid scans of the entire table. And you can get dramatically faster query speed on big databases by adding indexes. And so there's some SQL commands like take this form, create an index, you give it a name, and you basically say the table name and the column name. And once you run this, it kind of permanently adds an index for that column on that table, so that later on when you do queries, those can be faster. This doesn't like change the data. This indexes don't change data. They add metadata, which is to say, data about the data that helps queries be faster. Okay. So here's a picture showing one table. So this is an imaginary person table, has social security numbers, first name, last name, birth year. And if the social security number column is the primary key, then there'll be some kind of index created for it. There'll be some like tree structure, for example, that organizes all the social security numbers such that you can do like a quick traversal of this tree, which is like a binary search, to find particular numbers quickly. And then when you find those, so if you're looking for a particular social security number, you would use this in the database management system. By the way, all this stuff is like the details of this, like the way the trees are used, is invisible to you as a database user. All you do as a database user is write queries the way you've always have been, but also create indexes with like these simple like one-line commands. But then you have to know when to create the indexes, and that's kind of what this lecture is about. So if you were looking for all the people with a certain social security number, or the person with a certain social security number, like this purple query, select star from person where SSN equals this number, the database management system would use this tree to quickly find the node that has that number, and if there was one, it would have a reference to the row in the database that had all the details. And so it would be able to do only a few accesses to the storage to read out the data in these different nodes, and to finally get the address in storage where it can find all the details for that person. Okay. But importantly, you can have more than one index. So if you also index the birth year, that would be another tree using different values. In this case, all the values for birth year in the table, and there'd be like some middle value at the root. And you could traverse that to find details about those years. So these years would point to rows in the person table. Okay. And there probably would be, you'd have multiple entries for each year. So when you got down to 1960, you might have to these might be connected to other ones, and there would be many different references. But again, the details are not super important. Okay. So multiple indexes. And unlike the, these aren't sorted lists. They have structure and they're organized in a way that lets you find things. And there is some sorting in here in the sense that the left child is always less than the parent, and the right child is always greater than the parent. But it's not sorted in the sense that it's not laid out in storage in a sorted manner. And because of that, you can easily add and remove things without shifting. Okay. You can also have composite indexes, which actually operate on two columns together. So in this case, I have an index on first name and last name. And so it allows you to take those values together and look for matches in the database. And that would be useful for queries that check both of those. Like, for example, select star from person, where first name equals Alice and last name equals Sanders. An index, if you had indexes separately for first name and last name, those wouldn't really be enough to give you a really efficient solution to this query, an efficient answer to this query. Because they would give you separately a list of all the Alices and a list of all the Sanders, which is helpful, but that still could be like hundreds of people in both cases that you'd have to check for the intersection of those two sets to find the real answer. Whereas a composite index here could, in like one shot, give you precisely the one person or a few people that have that combination of names. Okay. So there's a difference between having multiple indexes and having composite indexes. Yeah. All right. So when running queries, so the whole point of this lecture is about performance optimization. If you have a query that's slow, you could try just guessing why it's slow and adding indexes to fix it. But there also are some tools that help you, give you information about what's happening that would guide your choice of indexes. So a query execution plan is like a set of steps the database management system is doing to implement your query. So if you write some select query, that tells what you want to see. It doesn't really say how to get it. The database management system has to somehow come up with a plan for like which table it's going to look at first, what's it going to look at next, and what is it going to use any indexes. You can actually see those query execution plans by running these special commands. Like basically, so on SQLite, you could say explain query plan, and then you put your select statement. On MySQL, explain, and then the query. And this tells you like what tables it looks at in what order, how many rows it's going to look at, and that helps you to pinpoint why a query is slow. Okay. So for example, on SQLite here, if I have the simple query select star from agents, where agent ID equals 2, if I just add explain query plan in front of that, then it prints out this little piece of information. It says that it's going to do one step. The first step is search table agents using index SQLite. Like this is the name of the index here, and it has the column name for the index. Whereas you'll see that's different than if I didn't have the where clause at all. Right. So let me actually copy the whole thing to another line. So a simpler query here that doesn't have a where gives a different query execution plan, which has one step again, but that step is different. The step is to scan the table agents. And scan means it's going to look through the entire table. So we should expect this scan to be slower than the search using an index. Okay. And we could also change this one to like if we used a different column in the where, so like say first name, so these two queries are similar looking, that they both select from a table and they both have a where clause. But the second one, because I'm checking to see whether the agent first name is William, it's going to do a scan table, which is different than what, again, the second one, let me see. The first one has this search table, not scan table, and it's using an index. And so this first one's going to be a lot faster. We won't notice it to be perceptibly faster on this machine because it's a small database anyway, so it's not taking much time to do anything. But the first one uses an index because agent ID is the primary key of that table, and therefore there's an index to quickly find rows according to that column's value, right? So I can take this 2 here and use it to traverse like a tree or stick it into a hash table or something to find just the rows that match that value. Whereas for first name, this is not indexed, it's just a normal column in the table. So there's no like shortcut for me to find the rows that just match that first name. Okay. On a bigger database, so here is MySQL. You'll use this. Sorry, it's a little bit small. Is there a way to make it bigger? Okay, I don't know about the font, but so this is actually, let me switch to the Stack Overflow database since we were talking about it. So that's so the Stack Overflow database has these tables. Like, okay, here's one called users. Okay, so the users table describe is a command that only it's on MySQL that like lists out the details of a table. So here are the columns for this table. So the users have like an age, a location, reputation, an ID, display name. Okay, and the primary key in this table is the ID. You can tell because it says pry over here by key. So there's only one column that's indexed on this table, and it's the ID. So if I want to get the information about a particular user, select star from users where ID equals like some number, then that would happen quickly. So you can see down here that took 0.08 seconds, and it returned this person called Orion Edwards in New Zealand, and they like .NET, C++, or Ruby, and whatever, right? That was fast. And the reason it was fast is because the thing we were checking, ID, is a primary key. And there's actually a little thing in this interface where you can see the execution plan graphically. So this is even better, actually, than explain. But this little picture tells you that in order to execute this query, it looked at the users table using a primary key, and it only got one row back. It's a little bit, it's not super intuitive, but there is some information there. Whereas if I wanted to do a query using some other information, like let's say account ID, if I want to find the user where the account ID is 234, and I run it, it's still running. It's going to take a long time because it has to scan through all the users to look for that particular account ID. It's still going. Okay, so that took 12 seconds to run that. And the result looks very similar. It's just one row. But even though the result was still one row, it took a lot longer because it took a lot longer to find that one row. And if we look at the execution plan, you see the picture here shows that it did a full table scan of users, which includes 7 million rows. So I had to check 7 million different values before finding the particular row that matched this criteria. Make sense? Okay. So as a database user and designer, so you're going to be running queries, and if you find slow queries, it means that there's an index missing, I guess, that you need to add. I mean, if you wanted that query to be faster. You don't always need the query to be faster, but if it's a query that you're running a lot and it's taking a really long time, then you'd want to add an index to make it faster. And you can do that by looking at the query and figuring out like what is it testing, and how is it narrowing down tables to specific rows? Using like what are the criteria for doing that? What columns is it checking? For example, if there's a where condition, that to filter down to specific rows. Whatever column is involved there should be indexed to make it faster. Also, a little bit more tricky than that is joining. If you're joining two tables, you can look at the on condition as something that needs to be matched between tables, and therefore define the match. If you want to find that match without doing a full table scan, then you would want to have an index. If you're joining with a foreign key, actually, then foreign keys require generally a index on the thing that's being matched to. So remember, a foreign key is a column whose value has to be the same as the value for a row in another table in some column. In order to make sure that that's true when you're doing an insertion, to enforce that foreign key constraint, database management systems require you to have an index on that second thing that's being referred to. So if you're doing a join on a foreign key, then it should be fast to begin with. You also might find if you're doing some kind of an aggregation function, like minimum or maximum, it may not be totally obvious to start, but you can use an index to figure that out. So similar, just like in a dictionary, I can easily find the word that's first or the word that's last by just flipping to the beginning or end. It's organized that way. So you can find the minimum and maximum words very easily in a dictionary. Similarly, you can find the minimum or maximum values for any index column by using that tree structure to kind of like go to one side of the tree or the other. So for example, in the same example, if I'm in this user database, so again, I can get the particular user ID, one particular user ID very quickly. I can also get the maximum of user ID. I can get that quickly as well because there's an index on it, right? So this tells me the maximum user ID is like 8.5 million, and that result came in like 0.01 seconds, okay? Because there's an index. And again, in the execution plan, you'd see that actually it it did seem to not even do anything for that one somehow. But if I wanted to count up, if I use a different aggregator like count star from users, this is slow because it requires a full table scan to count all the elements, I guess. Although it might depend on the type of index you have. So this gave a result of 7.6 million, and it took almost 3 seconds, which is kind of slow. Okay. Any questions on indexes so far? All right, so one thing to keep in mind is that indexes aren't free. I mean, we've talked about the benefits of indexes, but there is a cost. So you shouldn't add them unless you really need them. So a rookie mistake is to just index every column just in case. The problems with that is that there's both storage and performance overhead. So remember, all of these trees are going to have elements. The number of elements in these trees is going to be equal to the number of rows in the table, so it's not an insignificant size. And you'll need a new tree for every index if you're using trees. Whatever, every index consumes space that's proportional to the number of rows. There's storage overhead. There also is a performance overhead because whenever you add data, you have to update these indexes. Now, the performance cost is not as great as like when I talked about the pure sorted lists where we shifted everything over. That was a huge cost, like an order n cost for one element. But even if you only have to make a few changes, if those few changes are multiplied by the number of columns when you're updating a row in a table that has many index columns. Okay, so indexes can slow down modifications, although later on queries should be will be made faster by those indexes. If you don't take advantage of the indexes, though, you're never really gaining anything on the queries. You're just adding a cost for adding data, and both a performance and a space cost. Okay. All right, so I think that some of the terminology here is a little bit confusing because keys and indexes are kind of the same thing, but not really. So a plain key without any other word in front of it is the same as an index. It's just a way to find a row quickly. All right, so if you want to just make access to a table according to a column efficient. You can add what's called a key or an index. And then there are other specific types of keys that do have a search tree, a tree-like structure for indexing, but also have additional constraints. Like, so a unique key is an index that not only is able to find things quickly, but it prevents duplication, right? In order to prevent duplication, you want to be able to quickly find things that have certain values. So this would be a tree where the bottom level of the search tree has no repeated values. A primary key is a unique key, but there can only be one primary key per table. So that's a pretty simple concept, but and again, it's a different term, so it's kind of confusing. The primary key is kind of like the most important unique key in the table and the required unique key of the table. A foreign key is a column value that must match a column in another table. And in this case, the column you're referring to in that other table has to be indexed in order to quickly make sure that you're adding a valid value to your table, to the first table. Okay, so if I say that I'm adding a recipe ingredient, and it's saying that recipe 3 has ingredient 5, those are both foreign keys because like 3 refers to the recipe table, 5 refers to the ingredient table. I want to be able to quickly make sure that those numbers are valid recipe, like it's a valid recipe and it's a valid ingredient. And so in those two other tables, there have to be indexes to quickly find those the 5 and the 3. Yeah.
So that idea of a composite primary key,
Uh-huh.
is that just there's a unique key and a primary key?
Composite primary key. So I guess you could further extend this list to include composite unique keys, composite primary keys. All these things can be composite, I guess. Indexes can be composite, unique keys can be composite, primary keys can be composite, and foreign keys can be composite. The only difference is that instead of applying to one row, it's applying to multiple rows. So you kind of like take those rows and smush them together before doing whatever it is that you're doing with it. So like if you have a composite foreign key, you're making sure that 2 values from a table together match 2 values from another table, like a row that has those 2 values in 2 of its columns. As an example. Okay. Actually, let's spend a little bit more time on this. Okay. So on the midterm, we have some SQL queries, so might as well just use those as examples for figuring out how indexes would affect queries. Okay, so like here on question 1, which column would have to be indexed, or columns would have to be indexed to make this fast? So we're working with one table, staff. I guess that shouldn't have been all caps. Staff table, it has a position column and a salary column and these other 2 columns, the first name and last name, that are being used. So on which of these columns is indexing relevant, I guess, for this query? Position? Why? Yeah, so we're trying to narrow down our results to just those that have a particular value for position. Sorry, it's an obvious. Maybe it's a weird question, but obvious answer. But in order to quickly do that narrowing down of just the rows that have that particular position, we can use an index. Otherwise we have to scan through the whole table to look at everyone to figure out which ones have the faculty position. What about first name and last name? Would an index affect the speed of on those columns affect the speed of this query? It wouldn't. Would not, because we're just reading off those values from the rows that match this criteria, the position being faculty. Of course, we're also using salary over here, though. So the salary, is salary affected by indexing? If we were to index salary, would that affect our results? Salary is a number, yeah. Just like, so I guess so far we've talked about like words, text, and like alphabetical ordering. But the same concept applies to numbers. You can order numbers by their values. So if we had an index on salary, would that affect our answer? Like maybe? It depends, actually. So if okay, it depends on the query execution plan. All right. So to answer this question, we could first filter out all the faculty, and then sort them by salary. The thing is that the index of salary doesn't help us to sort out the subset of just faculty, because the index on salary applies to the whole table. So we might think that it wouldn't help. On the other hand, we could use a query execution plan that started off with salary. Like, for example, if you have a really big list of staff members, and you could look at just the top 20 salary people, right? And if most of them happen to be faculty, you could start off there with 20 and find the top 5 faculty from that 20 quickly. Like, for example, if there was no index on position at all, that might be a strategy the database management system could use to get some efficiency. It's not guaranteed to work in one step, because it could be that those top 20 don't include any faculty and you have to expand it to like more than 20. But it's possible here that indexing salary would help you to find the salary with the highest, the faculty staff with the highest salary. Okay. What about this second one? Select the students where the major is or find the proportion of students who are English majors. I guess was this one. What are the important columns for indexing? You have 2 tables now, students and majors, right? So are we doing any filtering here? Kind of. There's no where clause, but there still is some filtering. Like this summation here applies only to rows where the major is English. So if your database management system was clever enough, it would know that it could filter out the rows where the major is not equal to English, and it could kind of translate this into a count of the rows where the major is English. So an index on the major column would help you quickly find those rows. So major is one that, where an index would help. You also need to join these two together, students and majors, using major ID equals student major. So how can you make that faster? I guess we have student major is here, major is here. So this major table already has a so we can quickly find majors in this table according to their ID. But we cannot find majors quickly according to the name of the major, and that's why we mentioned adding an index here to make that fast. In reality, this is a short table, so it's not too important. we can quickly find the ID associated with English pretty quickly. But over here in the students table, if we want to filter out these students to have the right major, then an index on the student major column would be really helpful. So indexing that would help. Now, this is a little bit of a, there's some guesswork involved here, because I don't really know ahead of time what steps the database management system will take to execute the query. In other words, I don't know what the query execution plan will be. However, that's where you can use these kinds of tools to check the query execution plan. And then, looking at this, if you see a full scan of a table or an index, then that means that's an indication that something is slow, and you should try to add some kind of an index. Okay. All right. I guess I'm going to wrap it up there. We talked about how real databases, the kinds you'll encounter in internships and in work, will have many terabytes of data, not just these tiny ones we're working with in class. So far in class. So it can take hours or days to scan through all that data, and you don't want to do that. So you want to avoid these full table scans if at all possible. Indexes on columns allow rows with particular values to be quickly found. And so if you have n rows, you can use an index to find that a particular data row in log n time instead of having to go through every single one. You can kind of use a divide and conquer approach to very quickly find the particular data of interest. Tables can have many different indexes, not just one. So primary key introduces an index on that column, but you can add additional secondary indexes, and you can choose those columns that are indexed based on what kind of queries you expect to run on that data set. Okay. We can also have composite indexes that operate on multiple column values together, and primary unique keys are indexes, and foreign keys require an index on the thing that they're referring to. Okay. So see you next time. That's it.